Hi folks, this is my lecture on chapter 21 in your Brown textbook, nuclear things, and we're going to start by discussing the nature of the nucleus, which when you're thinking about the nucleus, you've got to remember, number one, that it's very small and very dense, and by very small, we're already thinking of atoms as being very small, right? So you're like, okay, it's smaller. But it's surprising how small the nucleus is compared to the overall size of the atom, in the sense that for your basic atom, if you have the atom and the nucleus, you're like, oh yeah, it's like a tenth of the size. It's not a tenth of the size. It is each atom, if you took a hydrogen atom, and you're thinking about your 1s orbital there, and you've got your nucleus in the center. Within the space of the 1s orbital, you could hold about 3 million hydrogen nuclei. And that's true as you scale up because your electron space gets bigger and your nucleus gets bigger. But if you can hold 3 million of them in there, that's very small. In terms of density, atoms are mostly empty space, right? So, you've got the nucleus, which is dense, and then kind of the electrons swirling around. When you're talking just about the nucleus, it's not mostly empty space, it's extremely dense. And I don't know where I got this calculation, but I love it because the density of a nucleus is 100 trillion elephants per cubic meter. So there's a cubic meter, and you fit 100 trillion elephants of mass in there. That is approximately the same density as the density of a nucleus. So that's cool. It's all positively charged in there. You've got a bunch of protons. You've got some neutrons that separate the protons to some extent, but there's no negative charge inside the nucleus. And one thing that you've probably wondered, and I've heard a lot of people wonder when they learn about the nucleus, is, well, there's a bunch of pluses in there, and pluses repel each other, right? So you kind of go, well, why aren't they repelling each other? And this is actually a thought that has been thought of by famous scientists in the past, including this Japanese dude, Hideki Yukawa. And he said, well, look, they should be repelling each other. With all of that positive stuff near each other, they should be exploding apart like craziness. And in fact, we can calculate exactly how much force there is between all of these protons that are pushing them out, and it's not exploding. So there's some force that's equally as strong pushing them in. I mean, I know it's there. There it is. Must be a force. And they named it the strong nuclear force, which I think is awesome. And that's the force that those protons and neutrons are being pulled together with. And actually, they found out later, in more like the 1970s, that one of the funny things about this strong nuclear force is it has a very short range. After you get past a certain distance, it kind of falls off really fast, and the strength of the strong nuclear force is no longer strong. Whereas with most of the forces, it kind of curves off. The strong nuclear force goes poof. And that's related to the fact that the strong nuclear force has something to do with the quarks and the gluons that make up the protons and neutrons, and it's sort of more complicated than I understand, so I won't explain that part, and it would blow your mind, I'm sure, even if I did. But there you have it. It's got to do with quarks. All right, so that's what the nucleus is like. You've got all these protons padded by neutrons, and the thing that you get interested in nuclear science is not the happy nuclei, but the unhappy nuclei, the ones that are unstable and have a tendency to fall into pieces of some kind. And that's called decay. When you've got a nucleus that doesn't stay in its state, it shoots off various things and falls apart, and that would be a nucleus that is radioactive. A radioactive nucleus has a tendency to decay because it is unstable. And the reason for this instability is basically its basic makeup. You've got to have a pretty precise ratio of neutrons to protons in order to make your nucleus happy. The reason for that being, we understand there are all these protons and they need to be, you've got the strong nuclear force keeping them together, but if there aren't enough neutrons kind of padding the protons, then that force isn't strong enough to counteract the electromagnetic repulsive force of pluses pushing away from pluses. So you need to have a good number of neutrons in there to keep the protons a little bit separated. And the other thing is that each of the particles in the nucleus, each proton and each neutron that you add to the nucleus, adds a little bit more strong nuclear force because it's carried by the presence of the particles in there. So if you got more protons in there, you've got more quarks in there, which means you have more gluons in there, and the gluons are the sticky things. Anyway, so if having more neutrons in there allows it to stay together better without adding more pluses, which would make it fall apart more. So then you kind of ask yourself, okay, well, that means you need to have neutrons in there. Well, can't we just have like more and more neutrons? And the answer to that is no, which is kind of the reason for that is kind of cool. First of all, the reason for that is you end up, if you had a nucleus where you had a few protons that were very highly separated by a large number of neutrons, you don't really need that many. You only need enough to where the strong force is perfectly balanced by the electromagnetic force of repulsion. And so, you have sort of an unnecessary number of neutrons. Well, why can't they stay there anyway? It's because the neutrons are a higher energy particle than a proton. And what's crazy is that neutrons can turn into protons and protons can turn into neutrons. And we'll get down to that when we talk about the types of decay. But because of this ability of interconverting between neutrons and protons, the higher energy, more massive neutrons are capable of, if there are too many neutrons, just kind of going bloop and turning into a proton. And so you can't really get a stable nucleus that has a few protons and a whole bunch of neutrons, because what ends up happening is that the neutrons will flip into protons. And that form of decay is beta decay, and we will talk about beta decay in a little bit. What's cool about that is, the neutron is more massive than the proton, and it can turn into a proton, which it has less mass. It's got more mass. The neutron has more mass, the proton has less mass. The neutron is therefore more energetic and the proton is less energetic. And what we're talking about here is E equals mc squared, where if you've got something that's more massive, it can flip into something less massive by sending off a small amount of that mass as energy. So that's very cool. And then the thing that I've mentioned before, another reason that you can't just cram, 600 neutrons into a nucleus is because of that strong force only being strong at short distances. And when I say short distances, I mean really, really short distances, because we've already talked about how small these nuclei are. Once you get bigger than 208 nucleons is the general term for dudes that live in the nucleus, and so it applies to protons and neutrons. So once you get bigger than 208 nucleons, your strong force, you've got that distance across. It's like the belt that you're using to hold the nucleus together isn't long enough to surround a larger nucleus, so it kind of goes blah. And your atom, when it gets that big, will fracture into two big chunks. So it will fracture and you'll form two new atoms. And the term for that is nuclides. You'll have two new nuclides. And that's called spontaneous fission if it just kind of gets too big and then it goes plah and breaks into chunks. So now I would like to go and look at this chart. Where is my chart? Here's my chart. This chart shows all of the stable nuclei. that they have been able to identify, and they're actually identified based on color how stable they are. So if you look, and this is actually flipped opposite from the way it is in your notes because I'm on the black pen screen, but anyway, if you look, there's a line, I need to label these x's. This is the number of protons, and this is the number of neutrons. N indicates neutrons, right? This Z comes from, I don't know if you remember this, but if you have some random element, and it has, it's got a top number and a bottom number, and the top number is your mass, and the bottom number is your atomic number. And these two numbers, they're represented when you're using variables as A and Z, your mass being the combination of neutrons and Z, the number of protons. So anyway, that's why they have this labeled as Z. So they're showing you this line here, which is the slope of 1, right? Where if you've got 20 protons, 20 neutrons, if you've got 60 protons, 60 neutrons, 100 protons, 100 neutrons. And what you can see is that at the beginning, you've got your stable nuclei kind of following the 1-to-1 ratio. But as you get bigger, it kind of swoops upward. You actually have sort of a curve in terms of the nuclei that are stable. And I don't know if I've explained this quite yet. Each of these little pixels is a nucleus that has been observed to be stable enough to exist. So, for example, let's pick one that's over on the edge and easy to find. So like this one right here. That is a nucleus that has like 51 protons and 49 neutrons. And that looks like, let's see, it's a yellow one. And so over here on the yellow, you can sort of see that this is the half-life. That's how long basically it will last, and I'll talk more about half-life later. The half-life of that nuclide that I just discovered on this chart here with 51 protons and 49 neutrons has a stability of about half a second, which is not very stable. So that's a very radioactive, decay-prone nuclide. And the reason for that is because the ratio of the protons and the neutrons is not good. There's approximately the same protons as neutrons, and when you're getting at the very beginning, that's good, but as you get bigger and bigger, you need more and more neutrons. So a nuclide up here, for example, you've got something like 110 protons, and for 110 protons, as stable as you can get, let's see, 110 protons, the stablest ones are like up here, which is like 170 neutrons. So you end up needing more and more neutrons as you go. So you can follow the stable ones. The white ones are the nuclides that are not radioactive at all. Whereas the colors here, the blue, pink, orange, yellow, and black, the black doesn't exist at all, and these have got some sort of half-life. So if you've got a light blue one, for example, this one, here's a nice light blue one, you've got about like 77 protons. If this were bigger to scale, we'd be able to see it better. 77 protons and like 88 neutrons. You can see that you're padding those protons a little bit more with extra neutrons as you go along. So it's interesting to note that the Z equals N line, it swoops off of that over time. So this side of it is, if you had nuclides on this side of this swoop here, so here's the main swoop, down here you've got too many protons. And up here you've got too many neutrons. And so if you have got some kind of, let's say this one here, this guy here suffers from too many neutrons, and so it's going to undergo some kind of decay that will cause that nucleus to move towards the stable range, which is going to decrease the number of neutrons relative to the number of protons. So you can either fracture off into a couple of chunks, or you can convert a neutron into a proton. But that's how you would get to from the top side of the stable line. Whereas if you're down here, if you had this guy here, for it to decay, it's got to move towards that stable line as well. That's too many protons. You can either turn a proton into a neutron, or and actually I'm getting ahead of myself. I need to get to the types of decay. So you can do something that would cause you to have more neutrons, and one of those options is to turn a proton into a neutron. All right. All right. There are lots of types of decay, but most of you need to think of the types of decay as solving a problem that you have if you are a nuclide. And you've got fission, which is the breaking of a large nucleus into chunks, large chunks. Not just a single individual particle coming off, but maybe breaking into two big nuclei, or something like that. That's nuclear fission. It's called spontaneous fission if it does it without you bombarding it with neutrons. That's what this little equation here represents. And you end up having nuclear fission when your problem is, I'm just too big. Sometimes you've got a nucleus that's more than 208 nucleons, and so it's unstable, and it will eventually undergo nuclear fission. And you can have different half-lives, so that can happen relatively quickly or relatively slowly, depending on how stable it is. But here we have an example of a nuclear fission happening here. And this one is uranium-295, which is the 295. It's not 295. It's uranium-235. Wait a minute. Hang on. Okay, we fixed that. Yeah, it's uranium-235. Somebody can't add. It's probably me. So uranium-235. This is the nuclide that is used in nuclear power plants and atomic bombs. There's my phone. And this is an unstable nucleus, and so what we're showing here is this wouldn't be called spontaneous fission, because if it was spontaneous fission, this wouldn't be here. This is fission that has been sort of kick-started by whacking it with a neutron. That's what this indicates. And remember that your top number is your mass, which is composed of your protons and your neutrons together, and your bottom number, that Z number, is just your atomic number. So in order to find out the number of neutrons, you subtract the 2. And here we are showing that we are firing neutrons at this uranium. This is something that happens just by virtue of being near other uranium atoms, actually, because they'll decay and send off neutrons. So anyway, this guy is being struck by a neutron, and while it was already unstable, that precipitated its decay into barium and krypton. And another thing that happened is it also shot off 3 lone neutrons here. And what's interesting about atomic bombs is that starting with 1 neutron, which precipitates a nuclear decay event, you end up with 3 neutrons. Well, if you have a big clump of uranium, those 3 neutrons can then go and hit other uranium atoms, which can precipitate them to decay more rapidly, which can give off 3 and precipitate more. And so if you have a large enough piece of uranium, that's called a chain reaction. So the chain reaction occurs when you've got 1 decay, and then that gives you 3, and then that gives you 9, and then that gives you whatever comes after 9, 27, and then it just gets big really fast. So that's fission. This indicates this one is not spontaneous, but uranium does undergo spontaneous fission, but it would make different products in that case. So there you go. That's one thing that happens there. Oh, and then the other thing that you've got to notice is that all your tops add up, and all your bottoms add up. So you've got 235 in terms of mass and 1 in terms of mass. So 236 pieces of mass, and over here you add these up, 142 and 91, and 3 ones. You add those up and you end up with 236 in terms of mass. And on the left side of the arrow you've got 92 protons, and on the right side of the arrow you've got 92 protons. So the tops have to add up and the bottoms have to add up. All right, alpha decay. Your 3 really basic types of decay that you're going to run across quite frequently are alpha, beta, and gamma. The 2 slightly odd forms of decay are positron emission and electron capture. So let's talk about alpha decay. Alpha decay is another method for reducing the size of a nucleus that is too large. The reason for this is because this works because what alpha decay is shooting off a helium nucleus. A helium nucleus is 2 neutrons and 2 protons in a clump. So you end up with this symbol here, 4 and 2, and the little symbol is the little Greek letter A, which sort of looks like a fish. This type of decay, one thing that you've got to consider when you're thinking about radioactive decay is how bad it is for you, and how much it can penetrate stuff. Alpha decay is the weakest penetrator of materials. It can't penetrate your skin. Like if you're wearing clothes, then you're not going to be damaged really by alpha decay on the exterior. It does become a problem if you eat something that is an alpha particle emitter, because then it can get all into your gastrointestinal tract and stuff, or if it gets incorporated into your bones, which is a thing that has happened. If you have a radioactive calcium or something and it gives off alpha decay, that can be bad. But generally we're not really worried about alpha decay because it is easy to protect yourself against it because it doesn't penetrate very far. It doesn't penetrate very far because it's big. It's large compared to the other types of decay. All right, so that's alpha, and it helps for a large nucleus. Beta decay is our solution to this problem that I was talking about over on this chart. This chart here. When you have got too many neutrons, when you've got too many neutrons, typically what you'll have happen is beta decay. This is the process of turning a neutron into a proton. And the mass difference between the neutron and the proton is energy that is converted into an electron that gets shot off, which is sort of crazy, but we're talking about E equals mc squared again. That energy difference is equal to the mass of an electron. The symbol for this is the little Greek letter beta. So here you'll end up with beta decay, or the little symbol that you used in the balance equation is an E with a 0, indicating that it doesn't actually have mass to it, and a -1 here, because what we're talking about is turning a neutron into a proton. So when a neutron turns into a proton, you are getting this guy, and you'll see how that works in a little bit. So that's the little symbol for beta decay, and that helps you move that way towards the stable nuclides. Gamma decay, beta decay is medium penetration. Because beta decay is an electron, it can penetrate farther than a helium nucleus, the alpha decay. So beta decay is somewhat more alarming than alpha decay is. And you would have to take more precautions if you knew that something was a beta decay, was a nuclide that tended to have beta decay. The third typical type of radiation that you sort of worry about is gamma, and you've probably heard of gamma radiation. This is not really particles; it's photons. So this is from the electromagnetic spectrum, like the rainbow and radio waves and X-rays, and then gamma rays. So gamma rays are these really high energy. That should not say protons. We're going to change that to photons. really high energy photons, also known as gamma rays. And these tend to be released along with other processes because while these nuclides are trying to fix their particle problems, they're also trying to fix their high energy state problems. And so quite frequently with other forms of radiation, gamma radiation will occur. When you've got the balanced equations for the decay, sometimes you'll see the gamma decay included in there, and sometimes they won't include it. And the reason for that is it doesn't have any mass, and so it doesn't actually change. What you end up with. And the symbol is the little y for gamma. And if you do see it in a balanced equation, it'll have a 0 and a 0. So it doesn't change what particles you end up with. Just be aware it's very high energy. Gamma radiation is very alarming because it's extremely penetrating and very high energy. So this is the dude that gives you pretty serious cancer that you can't hide from. Unless you have some kind of bunker made of walls with 3 meters of lead. Which I have only got one of those bunkers, and I don't know how many people are going to be able to fit in it, honestly. So this is the sort of stuff that you would really be worried about if you were thinking about health effects after some sort of nuclear something or other. So there we go. Those are your 3 typical ones. Alpha for too large of a nucleus, beta if you've got too many neutrons, and gamma to solve your too high energy problems. So I know what you're thinking. You're thinking, so we have a solution for a nucleus that has too many neutrons. What is our solution for a nucleus with too many protons? There's 2. You've got positron emission and electron capture. Positron emission is typically what you would have happen if the nucleus is sort of small, and electron capture is typically what happens if the nucleus is sort of big. So if you're talking about like nitrogen or boron, you're dealing with positron emission. If you're talking about uranium or whatever, then you're dealing with electron capture. And the way these are written is, what's interesting about a positron is that a positron is the antimatter particle that is the exact opposite of an electron. So an electron has a certain amount of mass and has a negative charge. A positron has the opposite amount of mass and has a positive charge. And if you ever have a positron hit an electron, they annihilate each other and shoot off a bunch of energy, which is awesome. So this positron emission will help a small nucleus with too many protons, and the little symbol is actually the opposite of this guy. So you've got an E with a +1 and a 0. That is a positron, and that's for these small guys. For big guys, you have electron capture, and this is still an electron with the same symbol, 0 and -1, but this ends up on the left-hand side because you're capturing it. So, like, I'll give it away. Here you see you've got an electron on the left-hand side. That's the electron going into the nucleus. And here you've got an electron on the right-hand side. That's an electron coming out of the nucleus. So be aware of that. And so these are the 2 ways that you can help a nucleus that has too many protons. And let's see. What's cool about electron capture is that the nucleus that has too many protons is going, I have got to convert a proton into a neutron. Neutrons are heavier. I need some mass. I need some energy. And he'll just eat one of the electrons in his 1s orbital. Well, now there's a hole in the most stable position around this nucleus, and so the electrons from the 2s go blunk, and the electrons from the 2p go blunk, and the electrons from the 3s go blunk, and so you've got all these electrons going bloop, 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 when you have electron capture. And if you remember, electrons falling down in orbitals release energy. So electron capture itself isn't so bad, but when you have got the electrons falling down as a result, it releases X-rays. So electron capture is also sort of is dangerous to stand around nuclei that have this as their tendency. Whew. Okay. Do I need to talk about this anymore? I don't think I do. Some problems. This is one of the two kinds of problems that you'll see with this section on radioactivity. And honestly, these are really easy and kind of fun, so I'm excited about showing them to you. The other one you already know how to do, actually, because it's from our unit on kinetics, and that will be in my next lecture about nuclear stuff. So here we go. And this is something I've mentioned before. Your left tops have to equal your right tops, and your left bottoms have to equal your right bottoms. And you, let's see, that's the law of conservation of mass again, and your proton changes are accounted for. If you're changing your protons, you've got, you've changed your protons, they're marked down here, you've changed your protons, this negative one is indicating that, anyway, let's go balance them. So, here we go. We've got the left-hand side and the right-hand side, and your left tops have to equal your right tops. So we've got 222 has got to equal something plus 4. That's going to be 218. How'd you do that? It's magic. And then you've got your bottoms as well, which is 86 equals x plus 2. Ooh, that's 84. So you've got your numbers, and now you go, well, what is the element that goes there? Is that Elmo? Well, Elmo. Then you go to your chart and you look for number 84. Number 84 is this guy here, which is polonium. And so you write in po. So now we have a balanced equation which indicates that radon with a mass of 222 is decaying by shooting this guy off. Do you recognize that guy? That's right, that is an alpha particle. That means that this is alpha decay. All right, next one. 14 equals x plus 0. I got that one. That one's easy. And 6 equals x minus 1. 7. And heck, I even know what that one is. That's nitrogen. And you need to recognize this dude. This is a beta particle being shot off, so this is beta decay. And actually, I didn't mention this. One thing that's slightly confusing is that beta decay is sometimes written as beta minus decay because you're using the minus one. And then positron emission is sometimes written as beta plus decay. Just be aware of that. You don't see that very often, but that's a thing. So this is beta decay. And this one, 11 equals 11 plus 0, and 6 is 5 plus 1. So this is whatever the dude is that is a 0 and a 1. Ooh, I know. That is a positron. And so that is, hey, I was just talking about you. This is beta plus decay. This is positron emission. Positron emission. Alright, there's a song. And then this one, that shouldn't be negative, by the way. This one, 235 and 1, gives you 137 something, and this is very important to notice this. This says 2 neutrons. So really what we have is a 2 here. So 236 equals 139 plus x. And what that gives you is 97. And then you've got 92 equals 52 plus x plus some zeros, which gives you 40. And then you go, well, what element is number 40? Why? It's zirconium. So zirconium it is, and this type of decay is, this is fission. And in this case, again, it's not spontaneous because it was incited to fizz. All right, this one, we've got polonium, and it is eating an electron. So this is electron capture. which solves the problem of having too many protons. And the other way to do that, if you remember, is positron emission. So this guy and this guy had too many protons, whereas this guy had too many neutrons, which you probably recognize because carbon is normally carbon-12 and carbon-14 is kind of big. And so that's going to be 204 still, and 84 minus 1 is 83. So what element is 83? Is bismuth. And X-rays, and that is electron capture. So one thing that you need to notice is that you can have an electron on the left side, and that's electron capture, and that solves the problem of too many protons. And you can have an electron on the right side, and that's beta minus decay, which solves the problem of too many neutrons. And that's what you do, switching back and forth, making a proton into a neutron, you capture an electron. Making a neutron into a proton, you shoot one off. So there are your types. That's how you balance them. Be careful when you have more than one neutron because it screws up your numbers a little bit. Otherwise, oh, and be careful with the negatives. It's really easy to screw up the negatives. Don't mess up the negatives. But that's it. Thanks, folks.